Hello everyone and welcome back to my channel. We are going to continue our discussion on the geometry of the molecules with a little bit of extra electron around them. They're known as expanded valence shells. That means we need to look at the molecules that we have either 5 or 6 electron domains for them. Okay, and they're going to be a practice as well. Okay, so for the 5 electron domains, these are the ones that are the most stable. Electron domain geometry is going to be the trigonal bipyramidal arrangement, which are typically consisting of 2 trigonal pyramids that are sharing a common base. Now, unlike previous geometries, the electron domains in the trigonal bipyramid occupying 2 distinct types of positions. We can call them either axial or equatorial positions. Now, in your axial positions, the 2 domains are positions perpendicular to the plane of the molecule. And for your equatorial positions, there are 3 domains that lie in the same plane, forming a 120-degree angles with each other and 90-degree angles with the axial domain. So if you look at what I have for you, the picture, this is going to be the axial positions, right? And these are going to be your equatorial positions, okay? 120-degree apart from each other and 90-degree, right, apart from the axial ones. Okay, so let's take a look at the next page. Okay, now suppose that you have a molecule that has 5 electron domains, which is including either one or maybe more than one non-bonding pairs of electrons. Okay, now the question for you is, where do we need to put these non-bonding electrons? Do we need to put them on the axial or on the equatorial? That's a very good question, right? So think about it for a moment. Okay, so to answer this question, we need to consider how much repulsion we are experiencing when you place them in either of these 2 positions. Generally speaking, electron repulsion is stronger at 90-degree angles than at 120-degree angles just because they are closer to each other. So the wider the angle is, the less the repulsion is. Okay, so having said that, if you look at your equatorial domains, they're going to experience 90-degree repulsion from only 2 other electron pairs, the axial ones, so only 2. But if you have them on the axial domains, right, they're going to experience 90-degree repulsion from the other 3 domains, the equatorial ones, right? Okay, so since greater repulsion leads to increase in stability, non-bonding electrons prefer to occupy equatorial positions. One more time, non-bonding electrons prefer to occupy equatorial positions, where they experience less repulsion than they would in the axial positions. So bottom line, we always need to put them in our equatorial positions. Okay, so let me show you some examples on the next few slides. Okay, so this is a really giant table. That's okay, no panic. We're going to be looking at them one at a time. So this is for all of the 5 electron domains geometry, right? Your famous trigonal bipyramidal, right? Now, if I don't have any non-bonding domains, I'm going to get my perfect trigonal bipyramidal. I don't have any complaints here. We're good, right? Now, if you have one of your bonding domains to be a non-bonding domain, only one pair, then that is going to give us a seesaw shape or molecular geometry. The best example is SF4, and look at that. This purple part is presenting your non-bonding pair. And as you can see, you have it on your equatorial position, right? Not on the axial ones. Now, if I have 2 pairs of electrons that are non-bonding, again, I'm trying to put them as much as I can on my equatorial, right? Which is the example that I have for the T-shaped. This is ClF3. And if I have 3 non-bonding domains, all 3 of them are going to be still on your equatorial, as you can see here, which is the example of a linear molecule, right? So you've got another linear one because, yes, just look at these two bonds. They are nicely aligned in a form of a linear shape. That's what I have for xenon fluoride. Okay, so these are all the possible geometries that we have for the 5 electron domains. The 6 electron domains are going to be on the next page. So follow me on the next page. Okay, now we're going to be looking at the 6 electron domains. Okay, so remember, if we don't have any non-bonding pairs, we're going to have the perfect octahedral, right? And all of these bond angles are going to be 90 degrees, right? Now, if I have only one non-bonding domain, then you can pick any of these 6 and you can replace it with that because they all are equivalent, right? They all, like all of these 6 vertices are exactly the same. So you just need to pick one of them and replace it with your pair of electron, with your non-bonding, okay? And that would give us the square pyramidal shape. Now, if you look at your 2 non-bonding domains, right? Now, because we try to minimize the repulsion, we have to put them in the opposite side. So they must have 180-degree angle between the lone pairs to minimize the repulsion, which is going to give us a perfect square planar geometry, right? I hope that makes sense. Excellent. So I've got a practice for you. Look at the next page. Okay, so here's the question. Use the Vesper model to predict the molecular geometry of IF5. So the first step is always drawing the Lewis structure. We have I in a center, and there are 1, 2, 3, 4, and 5, right? Single bonds with all of these fluorine. Your halogen, your I, has 7 valence electrons, so I'm going to have a lone pair as well. And then you always need to put your non-bonding electrons here as well. Just be patient, right? I'm doing my best as fast as I can. There you go. So this will be your Lewis structure. And as you can see, you've got 6 electron domains, right? So there are 5 bonds and there's 1 pair of electron. And there's only one non-bonding, right? So that will be your square pyramid. So I'm going to have my I as my center. 2 of these fluorine are going to be into the plane. 2 of them are like out of the plane on the wedge. And then they're going to be one of them, right, on the stick. And then you always have your pair of electron here as well. Perfect. Okay, that's it for this video. Thank you very much for watching this video. If you like it, you can always give it a thumbs up. And by the way, if there's any comments, if there's anything that I need to be aware of that, please add them in the comment section. Take care of yourself. I'll see you soon on the next video.